So, hello, this is a presentation for a paper uh, submitted by us to Mediterranean Control Conference. This is a new format for me, so I hope whoever watches it is going to forgive me for any technical hiccups. So let us go into the paper. The paper is about convex optimization based method for stiffness design for a tensegrity robotic structure. So what is it all about? Well, in this presentation, we'll first go about discussing tensegrity models. They are conventional, but we'll quickly establish them to see what we are talking about. Then we are going to introduce certain approximations which are pretty important for the work. And next, we'll introduce our algorithm of stiffness design. After that, we'll see how it performs. So first, what is a tensegrity structure? Well, it is a structure of beams or rods connected via cables. Basically, the idea is that the structure is completely composed of elements which only work on which only receive loads in the axial direction. So the structure those structures have a lot of good properties, and those properties can be they are discussed at length in the literature, so I will spare a long discussion here. But a good ratio between mass and stiffness or foldability is to transport like one of the well-cited properties of those things. Okay, here you can see on the slide rods are drawn as cylinders and there are cables. So what we can do actually when we talk about stiffness design is we can change rest length of some of those elements. This depends on the exact robot, but for example, for a tensegrity structure which is for some tensegrity structure, you can control the length of the rods themselves. So what you can do is install, let's say, a motor in it and change its length using a linear motor, for example. For other structures, you can control rest length of the cables. That is also reasonably easy to imagine how we will do it. So controlling rest lengths of those elements, cables or rods, you can effectively change both the configuration, statically stable configuration of the structure, but also you can change effective stiffness of the structure. So this is a way to discuss how we can control stiffness of the structures. We change rest length of the elements, and this way we achieve a different stiffness. Okay, now what is the mathematical description of tensegrity structure? Well, it is very simple. It is completely based on the description of spring between 2 points in space. And on this slide you can see we have a stiffness coefficient, difference between the actual length and the rest length times the direction of the elastic element. So this is a very basic model. And the sum of those forces acting between nodes is supposed to be equal to 0. That is the condition for static equilibrium. We can easily define stiffness using as a partial derivative of those sums of forces acting on an element, on a node, relative to the configuration of the structure. So the change in force to the displacement. So that is the standard way of thinking about stiffness. Now we can now introduce a linear approximation of elastic forces. So why do we introduce it? We're going to use convex optimization tools And the force that we just discussed is strictly non-convex. We cannot turn it into a convex function using some kind of change of variables or anything, but we can produce very good approximations. Obvious approximation would be just a Jacobian, first two terms in Taylor expansion, but also we can do it manually using some geometric intuition. We have a different paper exactly on this approximation, how we can use it in forward and inverse kinematics. So I encourage you to read this paper. It is cited in this one. But the idea is that there are simple geometric interpretations of both of those components, and their sum gives us this final product. So it is easy to get this linear approximation as a sort of sum of two pretty simple components. Okay, but how can we actually discuss this? Well, first of all, before we move on, I just want to point out that this force can be written down then as a linear function of position and rest length of the cables. Okay. Now, here is a profile of approximation error that we achieve with our proposed approximation. So this is the difference between actual force and what we achieve. This is for one specific case. We can study it for quite a lot of different configurations, but basically this is the profile that we achieve. We fix one node and we move another one, and we see how wrong we are based on our approximation. And this is a Jacobian approximation. So this first two terms in the Taylor expansion. What we see is that this approximation, the error here grows a little bit quicker in these regions, but the region with zero error close to zero, is bigger. Here this region is smaller, but it grows slower. So this is more forgiving for if we are in this region. We don't accumulate error as fast. Whereas here, when we are relatively close to the origin, like to the position where the approximation point noted by green dot, we are better. Okay. So this is a previously proposed result. Now let us discuss the stiffness model. Stiffness model is actually pretty simple. It is simply a Taylor, first two terms again in the Taylor expansion of the exact stiffness model, except here, since stiffness is a matrix, those would be tensors, and they will be multiplied by parameters. It is easy enough to rewrite all of this in the vectorized form. So we can vectorize those matrices and we will get a matrix here, and vector here. But we don't have to do it. I mean, we can easily keep it in the tensor form. But there is nothing that cannot be done with the standard linear algebra tools here. Okay. So this is a linearized stiffness model. Next, using this model and previously proposed constraint, what we can do is simply write objective function using this model, and we can diagonalize this, or for example, this objective function aims to control only elements on the diagonal, but we of course could vectorize it or do anything else with it. For example, we could vectorize it, multiply it by a function which would choose which components we can control, etc. There are many possibilities, but here we just take diagonals from this matrix and compare them with our desired values. And all of this is subject to our static equilibrium constraints. So important detail is that static equilibrium has to be achieved. That is a part of the stiffness design. Of course, we don't have to think about stiffness design in static, but then we would have to define what exactly we mean by stiffness design in different when static conditions don't hold. Here we assume that they do hold. So this is our approach, and this is a simple quadratic program. Of course, here we have a norm rather than a quadratic form, but we can change it into a quadratic form easy enough. Or we can just feed this direct formulation into any solver which can do preprocessing, like CVX, for example. Now, we can verify that our algorithm produce, this is iterative algorithm, first of all, because we use approximations, so our solution will be approximation of the actual solution. We have to iterate in order to get a better result. Here we can show that our force error converges to 0 with a lot of approximations, but it converges very steadily, and this is a logarithmic scale. So this is error, force error. And same for stiffness. Our stiffness converges very fast, and we don't really need to go to those enormous accuracies. So this just shows how fast it converges. Now, I'm running out of time, so I will have to finish here. And thank you very much for watching. I hope you have a good experience at this conference. See you later.